Imagine waking up tomorrow and reading that astronomers confirmed Betelgeuse was going supernova. Not in 100,000 years, within our lifetimes. Imagine the headlines, the photographs, people standing outside pointing at Orion's shoulder, photographing a point of light they had ignored their entire lives because now it had an appointment. That has not happened. But the data coming off Betelgeuse right now does not look like a star with 100,000 years remaining. In late 2019, it dimmed so severely that supernova response protocols were updated. It dropped from the 10th brightest star in the sky to the 23rd. 2 to 4 times the mass of Earth's moon was ejected in a single event. The star recovered. And then the anomalies began. Pulsation period shifting, mass loss rate exceeding models, circumstellar shell structure inconsistent with what any steady-state model predicts. And by 2026, the astronomers who know this star best have begun describing their position with the word that gives you the most accurate picture of where the science currently stands. Quietly. They are quietly worried. Tonight we go through what Betelgeuse is, what the Great Dimming revealed, what the monitoring data has shown since, what the day it explodes actually looks like, and why the researchers watching it most closely have not found a reason to stop. If this is your kind of evening, subscribe before we start. It keeps this channel running. Settle in. Let's begin. There is a word for what Betelgeuse is. Supergiants are a category in stellar classification, but the word has become abstract through repetition, a label applied to an image on a slide in a presentation, easily read and immediately forgotten. The word does not do the work it should, so let's build it differently. If you swapped Betelgeuse for our Sun, Jupiter would orbit inside it. Not near the surface, not grazing the outer atmosphere. Inside it, somewhere in the outer convective layers, orbiting through plasma at thousands of degrees. The Earth would be submerged, Mars would be submerged, the asteroid belt would be submerged. Jupiter, the largest planet in our solar system, would be inside a star whose surface had not yet been reached. What you see as a point of warm orange light in Orion's shoulder is an object so large that the distance from its center to its surface is greater than the distance from our Sun to Jupiter. Light moves at 300,000 kilometers per second. To cross from one side of Betelgeuse to the other, traveling at the fastest speed anything in the universe can reach, takes approximately 7 hours. 7 hours at the speed of light. A commercial flight from London to New York takes 7 hours. The beam of light crosses Betelgeuse in the same time, but it covers a distance roughly 1.2 billion times longer than the Atlantic route. And from Earth, all of that crosses your field of view as a dot. That dot radiates 100,000 times more energy than our Sun every second continuously. This is the only reason it is visible at all across 700 light-years of empty space. A star identical in size to our Sun at that distance would be invisible to the naked eye. Betelgeuse forces itself into your awareness by sheer output. The color of that output is orange-red, and the color is telling you something specific. It is telling you that the surface is cool. Not cool by human standards, cool by stellar standards. Roughly 3,000 to 3,500 Kelvin at the photosphere, compared to 5,678 Kelvin on our Sun. The reason for the cool surface is the size itself. Betelgeuse has expanded its outer layers to roughly 700 times the Sun's diameter, spreading the same energy budget across an incomparably larger surface area. More area, same power output, lower temperature per square meter. The orange color is what enormity looks like. It is the star's size expressed in wavelength. Sit with that for a moment. The surface of this star is not a surface in any sense you have encountered. There is no boundary. There is no ground. What astronomers call the photosphere is a region where plasma transitions from opaque to transparent as seen from outside. Not a physical edge, but a statistical zone. Through this zone, from deep inside the star, enormous convective cells rise. A single convective cell on Betelgeuse spans a distance comparable to the radius of Earth's entire orbit around the Sun. One storm cell on this star covers more area than the path Earth traces through space in a complete year. Direct imaging has captured these cells. The Sphere instrument at the Very Large Telescope in Chile has produced images of Betelgeuse's disk, showing the bright tops of rising cells and dark patches where cooler material descends. The images change over months. The cells rise, radiate their heat, cool and sink, replaced by new upwelling from below. The surface is in constant large-scale motion. It is not decorative motion. It is the outward expression of the energy transport that keeps the star from collapsing under its own gravity. Betelgeuse has been doing this for approximately 8 to 10 million years. Our Sun is 4.6 billion years old. A star as massive as Betelgeuse, estimated at between 16 and 20 solar masses, burns its fuel at such a rate that it has used up most of its available nuclear energy in less than 0.25% of the time the Sun has been alive. It lives hard. It is approaching its end. It is already in the red supergiant phase, which is not a stable long-term configuration, but a transitional state, a star restructuring itself while burning through the final fuel it has access to. The red supergiant phase lasts hundreds of thousands of years before the star either explodes or begins its final collapse. What comes next will make sense once this has had time to land. Betelgeuse is also, by an accident of celestial geography that matters enormously, the nearest red supergiant to Earth. The Milky Way contains perhaps hundreds of red supergiants. Most of them are thousands of light-years away in denser regions of the galactic disk. Betelgeuse sits at 700 light-years in the same local arm of the spiral as our solar system, close enough to be studied in detail that is not possible for any other object of its type. This proximity is why it has received the level of monitoring attention it has, and it is why, when it eventually explodes, the event will be visible in full daylight from any location on Earth that can see Orion. What does Betelgeuse actually look like from different distances? This comparison, called the dimming sun technique, takes a number and walks it through human-scaled reference points to reveal what raw figures cannot. From Earth at 700 light-years, Betelgeuse is a warm orange point, one of the 10 brightest stars in the winter sky, but still just a point, not resolvable as a disk without a telescope. The colour is visible, the relative brightness is obvious to anyone who knows the sky, but the scale is not apparent. It looks like every other bright star. Move closer. At Saturn's distance from our Sun, roughly 1.4 billion kilometres, the Sun has already diminished from a warm disk to a fierce, brilliant point. Noon on Titan, Saturn's largest moon, looks like deep twilight on Earth. Now imagine Betelgeuse where our Sun sits. You would not be seeing a star from Saturn's orbit. You would be inside one. Saturn's orbit falls well within Betelgeuse's outer layers. The photosphere above you, plasma in every direction. Move to Neptune. 4.5 billion kilometres from our actual Sun, the Sun still dominates the sky, but looks like a very bright star, stripped of warmth, stripped of the sense of presence it has from Earth, still the most luminous point in a black sky, but barely, and from Neptune's orbit, with Betelgeuse centred where our Sun is, you are still inside the star. Neptune, the outermost confirmed planet, orbiting nearly 4.5 billion kilometres from the Sun, would orbit inside Betelgeuse's photosphere. The scale model is not a metaphor, it is the actual geometry. The the star you can find tonight in Orion's shoulder, which appears as an orange point indistinguishable to casual observation from hundreds of other bright stars, would contain the orbits of every planet in our solar system inward from Uranus. The combination of what it is and how close it is makes Betelgeuse unlike anything else in the night sky. And the combination of what it has been doing lately and how carefully it has been watched makes the current state of the science unlike anything the field has previously faced with this star. In November 2019, a brief alert circulated among variable star monitoring networks. Betelgeuse was dimming faster than expected. This was not alarming on its face. Betelgeuse had always varied. 2 known pulsation cycles have been documented and characterized across more than a century of observation. A shorter cycle of roughly 400 days, driven by oscillations in the outer envelope. A longer cycle of approximately 2100 days, thought to connect to deeper convective processes. Both cycles produced brightness changes. Both had been measured, modelled and accounted for. Variable star observers watched Betelgeuse as a matter of routine, the way a doctor monitors a patient with a known condition. You know the expected range, you know the timing. When the numbers fall inside the parameters, you log them and continue. The November 2019 numbers were inside the parameters. Barely. By December they were not. By January 2020, Betelgeuse had dropped from the 10th brightest star in the sky to the 23rd. Let that number register before moving past it. Not slightly dimmer. Not at the edge of its historical range. The 23rd brightest star. A drop of more than 1 full visual magnitude, which on the logarithmic scale used in astronomy represents a reduction in visible light output of approximately 2.7 times. A star that had been a dominant landmark in the winter sky was competing in brightness with stars casual observers had never consciously noticed. People who had spent years monitoring Betelgeuse stepped outside in January and February of 2020, looked at Orion and stopped. The shoulder was wrong. The professional response was immediate. The Hubble Space Telescope was redirected to ultraviolet observations of the disk. The Very Large Telescope Sphere instrument began a dedicated imaging campaign. Spectroscopic facilities on multiple continents collected high-resolution data. Radio and sub-millimeter observatories pointed toward Orion. Within weeks, Betelgeuse had become the most intensely watched star in the Northern Hemisphere. What were they watching for? That is the question nobody said aloud, in any official capacity at that point. A supernova. They were watching to see if this was the beginning of one. The probability assigned to that scenario was vanishingly small. The stellar evolution models placed Betelgeuse at thousands to hundreds of thousands of years from core collapse. An imminent supernova was not a serious working hypothesis, but vanishingly small is not the same as zero, and what was being observed didn't match any of the models that had successfully described this star's behaviour for the previous 50 years of systematic monitoring. The dimming was too fast, too deep, and too unlike either of the 2 known pulsation cycles to be comfortably dismissed. The star that should have varied within its known limits had stepped outside every limit the historical record contained. The historical record of Betelgeuse variability extends further back than most people realise, and the pre-dimming behaviour, examined carefully, carries significance that became more visible in retrospect. Long-term photometric monitoring of Betelgeuse by the American Association of Variable Star Observers extends back to the late 1800s. The dataset contains roughly 1 million individual brightness estimates from professional and amateur contributors across more than a century. Buried in that data are periods of elevated variability, times when the star's pulsation appeared more irregular than the baseline predicted. The 1836 and 1840 observations by John Herschel fall into this category. The historical record is imprecise by modern standards, but it suggests that the star's behaviour before 2019 was not uniformly predictable across its full history. The 2019 event was unprecedented in depth and rate of change, but isolated anomalies are not unprecedented in the longer record. The important distinction is between unprecedented within the modern monitoring era and unprecedented within the full range of the star's behaviour. What the 2019 event violated was the expected range defined by systematic observations over 150 years. Whether that 150-year window captured the full range of what this star is capable of, or whether the star has always been capable of more extreme events at lower frequencies than the observational record could detect, is a question the post-2020 science is actively investigating. Quietly, that is the word. The concern was real. The word quietly deserves attention as the organizing principle of what the Betelgeuse science community is actually doing, not loudly. The event was covered loudly in early 2020. The dimming generated headlines, social media discussion, speculative pieces asking whether the supernova was beginning. Professional astronomers responded carefully. The public attention was enormous for a few months and then moved on when the star recovered. The recovery was covered as a resolution. The story was treated as closed. The monitoring network that detected this change in 2019 was not built for emergency response. It was built for the kind of patient, sustained observation that accumulates data across years and decades without expecting a dramatic result in any particular observation cycle. The deviation from expectation was visible precisely because the baseline was well established. Without 150 years of prior observations, without the month-by-month photometric records going back to the 1800s, the 2019 minimum would have had nothing to be compared against. The anomaly is defined by the baseline. The baseline is the century and a half of quiet, unspectacular watching that preceded the event. The post-recovery anomalies have not received comparable attention. The papers documenting the pulsation period shift were read by the variable star community and cited within it, not amplified by mainstream science reporting. The circumstellar shell analysis, with its implications for elevated mass loss rate, appeared in journals read by researchers who work on stellar mass loss, not by the general audience that followed the Great Dimming story. The web findings from 2025 and 2026 reach the professional community and a small slice of science enthusiasts. The gap between what has been publicly prominent and what has been scientifically documented is substantial. The Betelgeuse that exists in most people's understanding, as of 2026, is a star that had a dramatic episode in 2019, recovered, and is now fine. The Betelgeuse that exists in the monitoring data is a star that has been accumulating anomalies since 2020 across multiple independent measurement types, all pointing in the same direction. Both of these things are true at the same time. The first is what was loud. The second is what has been quiet. The attention was fully engaged and the public statements were carefully measured, because what was being observed could still turn out to have a completely conventional explanation. It was too early to know, but the professional community was not comfortable. The explanation arrived over 2 years. It required 2 independent processes, not one. And the explanation, assembled from data across multiple instruments and multiple research groups, was not the simple, comfortable story anyone would have preferred. The short version became, dust blocked our view. The star ejected material, the material cooled and formed dust grains, the dust temporarily obscured some of the star's light. When the dust dispersed, the star returned to normal. Move on. The short version is partly right, but the part it omits is the part that has not stopped being relevant. The star sneezed a mass of hot gas larger than Mars's entire orbit, and the sneeze cooled its own surface. Two things happened simultaneously in late 2019. First, a massive convective upwelling in Betelgeuse's outer layers drove an eruption. The ejected mass was later estimated at several times 10 to the 24th grams. That is 2 to 4 times the mass of Earth's moon expelled in a single event. The material moved outward at several hundred kilometers per second. As it cooled in the lower pressure space beyond the photosphere, silicate dust grains condensed from the gas, forming a cloud spanning an area larger than our entire solar system, positioned between Betelgeuse's southern hemisphere and Earth's telescopes. The Hubble ultraviolet observations taken at the minimum showed exactly this. The southern half of the disk significantly darker than the northern half. Localized dust obscuring one hemisphere, that is the first cause. It accounts for roughly half the brightness drop. Second, simultaneously, independently, a large region of Betelgeuse's photosphere cooled by approximately 200 Kelvin. This is not a dust effect. This is the star itself radiating less energy from that region. The Stefan Boltzmann law governs the relationship between temperature and radiated power, and that relationship runs to the fourth power. A 6% fractional temperature drop produces a reduction in radiated energy of roughly 22% from the affected region. Applied across a substantial fraction of the visible disk, that is a genuine dimming, not an obscuration. Two processes, each real, each contributing roughly half. Neither alone sufficient to explain the record minimum. Let that settle before we go further. The research team that established this interpretation, led by Andrea Dupree and published in 2021, called the ejection a surface mass ejection, explicitly drawing the parallel to solar coronal mass ejections while noting the scale difference. Our Sun occasionally ejects material in coronal mass ejections large enough to disrupt power infrastructure on Earth. The Betelgeuse event ejected roughly 1 trillion times more mass. They share a physical mechanism. They differ in magnitude the way a garden hose and a burst municipal main share the mechanism of water moving through a tube. Now here is what the surface mass ejection actually tells you. A convective cell powerful enough to mechanically eject 2 to 4 lunar masses past escape velocity is not a cell operating in the normal range. The kinetic energy required to lift that mass against the star's gravity, after losing energy to the surrounding material on the way up, had to be delivered by a cell with enormous energy content at depth. That energy came from the stellar interior. The nuclear burning that powers Betelgeuse is what ultimately supplied the energy that drove the 2019 ejection, and an interior that delivers that much energy to a convective cell is an interior operating at the energetic extreme of what the pre-2019 models described as possible. The photospheric cooling confirms a related but separate point. The star's outer layers are not thermally stable in the way the pre-2019 models assumed. A large region of the photosphere cooled by 200 Kelvin, independently of the mechanical ejection, because the energy transport from below was temporarily disrupted in that region, not by the eruption. Alongside it, two separate systems failing in the same direction at the same time, combining to produce an event more extreme than either would have produced alone. Take a breath here. The broader significance of the 2019 event for stellar astrophysics extends beyond Betelgeuse itself. Red supergiants as a class are poorly understood in the details of their mass loss behavior, and events like the Great Dimming provide rare opportunities to observe mass ejection physics in a specific, well-characterized star. The classical picture of red supergiant mass loss assumed that stellar winds, driven by radiation pressure on dust grains that condense in the cooler outer atmosphere, account for the bulk of mass shed over a star's lifetime in this phase. Pulsations help push material outward to the radii where dust can condense and radiation pressure can take over. This picture, while broadly correct for the slow continuous wind component, may systematically underestimate the contribution of episodic mass ejection events of the type observed in 2019. If episodic events contribute a substantial fraction of total mass loss in red supergiants, the time-averaged wind-based models produce inaccurate total mass loss estimates over the full red supergiant lifetime. The circumstellar structure of Betelgeuse, as revealed by post-2020 observations, suggests that episodic events have contributed substantially to the mass surrounding the star. The multiple distinct shells, each requiring a discrete ejection event to explain their structure, are not what a purely continuous wind produces. A continuous wind produces a smooth, diffuse circumstellar envelope without shell structure. The observed shells require episodes of enhanced mass loss, concentrated in time, separated by longer periods of lower activity. Whether this episodic behavior is characteristic of Betelgeuse specifically, or of red supergiants, generally cannot be determined from a single star's circumstellar structure. But Betelgeuse is the closest red supergiant available for this kind of detailed study, and what is learned from it will be applied to the broader population. The mass ejection of 2019 thus serves as a case study for a physical process that may be important throughout the red supergiant phase of massive star evolution, not just as a late-stage phenomenon specific to stars near core collapse. Understanding it fully, which requires continuing to observe the aftermath and track how the ejected material behaves as it moves away from the star, is worth doing regardless of where Betelgeuse currently falls in its timeline to core collapse. The star recovered. The dust dispersed. The photosphere reheated. By April 2020, the brightness was rising. By late 2020, Betelgeuse was actually somewhat brighter than its long-term average. The public story closed. The headlines moved on. The instruments pointed at it did not move, because what the event had disclosed was not an explanation for why the star was fine. It was a disclosure of what the star's interior was capable of. And what it was capable of, evidently, exceeded what the previous models had described. The alternative interpretations of the Great Dimming, the ones that were proposed and examined before the two-cause picture consolidated, are worth understanding because they show what was and was not ruled out by the evidence. The single-cause dust interpretation, that everything could be explained by dust obscuration without any genuine change in the star's light output, was attractive in its simplicity. Betelgeuse had been known for years to lose mass through stellar winds and to have a complex circumstellar environment. A localized mass ejection forming a dust cloud was not an exotic proposal. The problem was the hemispheric asymmetry in the Hubble ultraviolet data. The southern hemisphere of the disk was darker than the northern hemisphere, in a way inconsistent with uniform global reduction in brightness. Something was blocking one hemisphere preferentially. That something was a localized dust cloud, not a global change in the star's output. But the measured brightness at minimum was too low to be explained by the dust alone given the degree of asymmetry observed. The other half required a second process. The single-cause cooling interpretation that a photospheric temperature drop alone explained the dimming without any dust contribution ran into the opposite problem. Spectroscopic temperature measurements during the minimum showed cooling consistent with a fraction of the magnitude loss, not the full observed depth. Cooling without dust could not account for the full drop. The two-cause picture was not convenient. It required two independent processes happening simultaneously in a time frame that made statistical coincidence the only alternative explanation. But the data from multiple instruments, analyzed by multiple teams, consistently supported it. By 2022, it was the consensus interpretation. What the consensus interpretation leaves open is the question of mechanism. Were the mass ejection and the photospheric cooling truly independent, Or did they share a common upstream cause in the convective activity of the star's interior? The most likely answer, based on the subsequent analysis, is that they share an upstream cause but manifest as two separable downstream effects. A very large and energetic convective cell rose through the outer layers of the star. Its mechanical energy drove the mass ejection. Its thermal wake, the disruption left in the region from which so much material had risen, produced the photospheric cooling as the normal energy transport from below was temporarily interrupted. Two downstream effects, one upstream cause, producing what appears in the data as two simultaneous independent processes. This interpretation, if correct, makes the 2019 event a single convective event of extraordinary energy, rather than a coincidence of two unrelated processes. That distinction matters for interpreting what the event says about the star's interior. A single ultra-energetic convective event is a statement about the amplitude of the convective motions currently operating inside Betelgeuse. It says those motions are capable of producing cells with enough energy to drive lunar mass ejections and simultaneously disrupt photospheric temperature stability across extended regions. That is more energetic than the pre-2019 models characterized the normal convective regime to be. The star recovered. The concern did not. Beginning in 2021 and building through 2025 and into 2026, the monitoring data from multiple independent research groups began producing a pattern. Not a single alarming finding. Not smoking gun. A pattern. A collection of measurements falling consistently outside the range the pre-2019 models predicted, all pointing in the same direction, all suggesting a star operating in a more extreme state than previously characterized. Here is what the data shows. The longer of Betelgeuse's two pulsation cycles, the approximately 2100-day oscillation, appears to have shortened. Multiple independent analyses of the post-2020 photometric record find a period closer to 1900 days. A 10% shortening of a pulsation period is not a rounding error. Pulsation periods are physically determined by the density, temperature, and composition of the oscillating region. They do not shorten spontaneously without a physical cause. If the period change is real and persistent, something about the deep internal layers changed during or around the 2019 event and has not returned to its historical state. The researchers documenting this are careful. The post-dimming baseline is still short relative to the cycle length. More complete cycles need to be observed before the period change can be characterized with full confidence. But it appears across multiple independent data sets. It is not an artifact of a single instrument or a single team. In 2023, spectroscopic monitoring of the star's radial velocity, the Doppler measured motion of the surface toward and away from Earth, found systematic deviations from the expected pattern of the long pulsation cycle. The surface was not oscillating on the schedule the historical baseline predicted. The deviations were consistent across multiple instruments. They did not average away with more data. In 2024, a comprehensive analysis of the circumstellar dust shells surrounding Betelgeuse revealed a layered structure considerably more complex than previous models had assumed. Multiple distinct shells at different distances from the star, each one recording a past ejection event, like growth rings in a tree but written in expanding clouds of silicate dust. The innermost shell from the 2019 event was already interacting with the next older shell, at roughly 2 astronomical units from the star's surface. The total mass in all detectable shells, combined with the timescales of the ejection events, implied a mass loss rate higher than what any steady-state model for a red supergiant at Betelgeuse's evolutionary stage would predict. The description in one paper, not consistent with steady-state mass loss models. In plain language, the model and the data disagree. The disagreement is not attributable to measurement uncertainty. Hold that for a moment before we continue. In early 2025, James Webb Space Telescope observations added resolution that ground-based instruments could not match. MIRI mid-infrared imaging of the circumstellar shells confirmed the multi-shell structure and showed the innermost and second shells in clear interaction. The Webb data also revealed a faint third shell, previously undetected, at a distance suggesting an ejection event roughly 100 to 150 years before the 2025 observations. That timing places the inferred event in the mid-1800s. John Herschel recorded anomalous variability in Betelgeuse in 1836 and 1840, noting in his observing journals that the star appeared unusually different from its expected character on specific dates. If the shell corresponds to an ejection of that era, the 2019 event was not an isolated anomaly. It was the most recent member of a series, each event large enough to leave a detectable circumstellar trace, each separated by decades to a century. In early 2026, further Webb analysis found the multi-shell structure most readily explained by episodic mass loss events of increasing frequency over the past several centuries, and noted that this pattern, if it reflects a genuine trend rather than stochastic variation, would be consistent with an object in a more advanced evolutionary state than commonly assumed. An object in a more advanced evolutionary state than commonly assumed. That phrase, in a peer-reviewed paper published by people who know this star's data in more detail than anyone else alive, is not casual speculation. It is the conclusion those researchers believe the data supports, hedged appropriately, falsifiable with more observations, but stated. The question of what changed in Betelgeuse during the Great Dimming event, specifically what physical change in the deep interior could have produced both the surface mass ejection and the photospheric cooling while simultaneously initiating the pulsation period shift, is one that the research community has not yet answered definitively. Several hypotheses have been proposed and are being evaluated against the ongoing observational data. One hypothesis involves a resonance between the two known pulsation cycles, the 400-day and 2100-day cycles, when their phases align in a specific way, could produce constructive interference, amplifying the amplitude of convective upwellings beyond what either cycle alone would drive. If the Great Dimming occurred at a phase of maximum constructive interference between the two cycles, the unusually energetic convective cell that drove the ejection could be explained without invoking a change in the star's internal state. Under this hypothesis, the long cycle period shortening observed after the dimming reflects the phase of the cycle at which the event occurred, not a genuine change in the period itself. The period would eventually return to the historical value as the resonance phase shifts. A second hypothesis involves a genuine change in the star's internal structure. If a substantial convective cell reached the photosphere with enough energy to briefly disrupt the normal pattern of radial pulsation, it could have altered the density structure of the outer envelope in a way that changed the resonant period of the long cycle. Under this hypothesis, the period shortening is real and persistent, a consequence of physical changes in the pulsating layers that the 2019 event caused. This hypothesis predicts that the period will remain shorter than the pre-event baseline for years and possibly decades, which is consistent with what has been observed so far. The distinction between the two hypotheses requires a longer baseline of post-event pulsation data to evaluate definitively. A third hypothesis places the disruption deeper in the star. If the 2019 event was driven by a change in the energy transport from a layer deeper than the convective envelope, perhaps a temporary reduction in the opacity or conductivity of an intermediate layer that briefly allowed more energy to flow outward, the effects would ripple through the outer layers in ways that could produce both the mass ejection and the period change as downstream consequences of an upstream structural shift. This hypothesis is harder to evaluate observationally because the relevant layers are even more deeply hidden than the pulsating envelope. What all three hypotheses share is that they make specific predictions about how the star's behavior should evolve in the years following the dimming. The continuous monitoring programs running since 2020 are accumulating exactly the data needed to test those predictions. The researchers running those programs are watching the pulsation behavior, the mass loss rate, and the surface velocity patterns for signatures that distinguish between the hypotheses. The answer will emerge from the data over the next decade or more, not from any single observation. The numbers are not settling. They are accumulating, and they accumulate in one direction. The circumstellar shell observations deserve more detailed attention because they represent the most direct evidence for the long-term mass loss history of the star, and that history is what makes the post-2020 anomalies most concerning when viewed in their full temporal context. Mass loss is fundamental to the late-stage evolution of massive stars. Red supergiants lose mass continuously, driven by a combination of stellar winds, pulsation-driven outflows, and episodic eruption events. The rate at which mass is lost determines how much material remains in the envelope at the time of core collapse, which affects the characteristics of the supernova itself and the mass of the remnant that forms afterward. Mass loss rate in red supergiants is one of the quantities that theoretical models have historically struggled most to reproduce accurately because it depends on physical processes, dust formation, pulsation-radiation coupling, magnetic activity, that are difficult to model from first principles. For Betelgeuse, the circumstellar observations provide a direct measurement of the integrated mass loss over the past few centuries, written in the shells of dust and gas surrounding the star. The innermost shell from 2019 is the freshest layer. The shells at intermediate distances correspond to previous ejection events. The outermost detected structures, at larger distances, record events from further back in the star's past. Reading this structure is like reading the rings of a tree, except that each ring represents a mass loss event rather than a year of growth, and the spacing between rings tells you about the interval between events rather than the passage of uniform time. The Webb observations from 2025 and 2026 resolved this structure at a level of detail that changed the picture. The three distinct inner shells, with the middle one newly detected, indicate that the 2019 event was the most recent in a series of at least three major ejection events over the past roughly 300 years. The estimated dates of the three events, 2019, mid-1800s, and perhaps 1600s to 1700s for the outermost of the three, suggest an interval of roughly a century between episodes. The 2019 event was the largest of the three. The middle event, inferred from the newly detected intermediate shell, was smaller but still large enough to produce a detectable circumstellar trace that persisted until 2025, when Webb resolved it. If this pattern is real and reflects genuine structure in the star's mass loss history, rather than statistical fluctuation in a continuous but variable outflow, it has implications for how the star's mass loss behavior is modeled going forward. A mass loss history characterized by episodic ejections at roughly century intervals, with the most recent and largest episode occurring in 2019, would suggest that the star's mass loss regime is dominated by discrete events rather than continuous wind-driven outflow. This is qualitatively different from what the standard models assume. The standard models treat mass loss as a quasi-continuous process, time-averaged over long periods. If discrete events at century intervals are the primary mode of mass loss, the average models systematically mischaracterize when and how the mass is lost, which affects the predictions for the remaining envelope mass and the eventual supernova characteristics. Whether the pattern represents genuine episodic ejection events or an artifact of particularly large fluctuations in a continuous process is not yet settled. The dataset from Webb is still being analysed. The interpretation is preliminary, but the structure is real. The shells are there, and their most natural explanation involves a history of repeated significant ejection events, rather than a smooth, continuous outflow. Every description of Betelgeuse eventually arrives at this question: when will it explode? The range in the literature runs from roughly 10,000 years to roughly 100,000 years. That range is honest. It is not a product of insufficient effort or inadequate instruments. It is a physical limitation in what can be learned about a star by looking at its surface without being able to examine its interior. Here is the sequence. Betelgeuse burns nuclear fuel in stages, each stage faster than the previous one. Hydrogen burning, which powers the main sequence, completed millions of years ago. Helium burning followed, producing carbon and oxygen in the core. After helium exhaustion, carbon burning begins, then neon, then oxygen, then silicon. Each stage releases less energy per unit of fuel. Each stage completes faster than the last. Carbon burning in a star this massive lasts thousands of years. Neon burning lasts about a year. Oxygen burning lasts months. Silicon burning lasts days. The end of silicon burning is the end of the star. The iron core grows, passes a critical mass, and collapses in approximately 1 second. The range is between 10,000 and 100,000 years, which means, by cosmic standards, imminently. A compressed timeline helps place Betelgeuse's situation in human terms. If Betelgeuse's 10 million year life were compressed to a single year, we would be watching it in the final 3 days of December. The star was born at midnight on January 1st. It spent most of the year on the main sequence, fusing hydrogen in its core, before leaving that phase in early December. The red supergiant phase began perhaps December 28th. The great dimming of 2019 occurred somewhere in the final hours of December 31st. The remaining 10,000 to 100,000 years of estimated lifetime, on this scale, fall within the last few minutes of the year. The star was alive for 364 days, and some hours before you could meaningfully call it approaching the end. It has been in its final phase for roughly 3 days of the compressed year, and it has roughly a few minutes left, by the lowest estimates, or perhaps an hour by the highest. This is not an argument for alarm. The lowest estimates are already 10,000 real years. But it illustrates what the final phase means for a massive star. The red supergiant stage, which might last hundreds of thousands of years, is still the last chapter. Everything observable about Betelgeuse from the outside right now, its colour, its pulsations, its mass loss, its circumstellar environment, is the behaviour of an object in the final chapter of its existence. Not the final sentence, perhaps, but the final chapter, by cosmic standards, not human standards. The distinction matters. 100,000 years is more than twice the span of all recorded human history, from the earliest writing to right now. It is not short by any measure relevant to human experience. But against the 10 million year lifespan of a star like Betelgeuse, 100,000 years is 1%. A star that has lived 99% of its life is, by any proportional measure, at its end. What cannot be observed from outside the star is which burning stage the core has currently reached. This is the critical limitation. A red supergiant with a helium-burning core and one with a carbon-burning core look almost identical from the outside. The surface temperature, the luminosity, the pulsation behaviour, the mass loss rate, all of these overlap in ranges that do not cleanly distinguish one internal state from another. The surface tells you about the surface. It does not transmit a direct report from the core. The only way to observe the core directly is to detect its neutrinos. Normal stellar fusion in a star at 700 light-years produces a neutrino flux too faint for current detectors to measure. Only the sudden, catastrophic burst of neutrinos from core collapse itself, releasing in 10 seconds more energy than the Sun produces in its entire 10 billion year lifetime, is detectable from that distance. The detectors exist and are running. SNEWS, the Supernova Early Warning System, links underground neutrino detectors on multiple continents in a real-time cross-correlation network. But those detectors will not tell you anything useful about the current internal state of Betelgeuse. They will tell you the moment the core collapses. Those are different things. The most recent theoretical modelling places Betelgeuse somewhere in late helium burning to possibly early carbon burning, implying remaining lifetime in the range of tens of thousands to perhaps 100,000 years. But those models were built before the post-2020 anomalies were fully incorporated. The elevated mass loss rate, the pulsation period shift, the circumstellar shell complexity, none of these have been fully integrated into the current best-fit evolutionary models in a way that has produced revised lifetime estimates the community considers definitive. The models are being updated. The updates are not yet complete. The stellar evolution models that produce the 10,000 to 100,000 year remaining lifetime estimate depend on several inputs that carry genuine uncertainty, and understanding those uncertainties explains why the range is as wide as it is. The distance to Betelgeuse is uncertain at roughly plus or minus 100 light-years, which propagates directly into the inferred luminosity and mass. The current mass is uncertain because the initial mass is uncertain and the integrated mass loss over the star's lifetime is uncertain. The internal rotation rate is inaccessible to direct measurement because the convective envelope conceals the core's angular momentum state. Each uncertainty affects the predicted remaining lifetime, and they compound rather than cancel. The only nearby supernova of the modern era for which pre-explosion imaging exists is SN 1987A. But its progenitor was a blue supergiant, structurally different from Betelgeuse, and the pre-explosion images were archival photographs not taken for monitoring purposes. No clear external precursors were detected in the years before the 1987 explosion, with the instruments and cadence available at the time. This does not mean no precursors existed, it means they were not captured. What would have been visible with 2026-era instrumentation pointed continuously at that progenitor in the years before 1987 is unknown. Betelgeuse will be the first massive star in the modern era to be monitored with this intensity before its eventual explosion. Whatever sequence of events precedes its core collapse will be observed by the instruments currently running. Whether those observations will reveal clear precursors that could have been predicted from physics, or whether the transition will appear sudden even in hindsight, is one of the most important open questions in observational stellar astrophysics. The data being collected now will answer it. What the post-2020 data cannot do is move the remaining lifetime estimate confidently inward. What it cannot be used to do is rule out the lower end of the existing range. The lower end of the existing range is 10,000 years. 10,000 years is not imminent by any standard a human being normally applies, but it is a very different thing from 100,000 years in terms of what it implies about the current internal state of the star. The stellar evolution models that produce the 10,000 to 100,000 year remaining lifetime estimate are worth understanding in more detail because the estimate and its uncertainty reflect genuine complexity, not simply a failure of precision. Stars at Betelgeuse's evolutionary stage are modelled using codes that track the composition and physical state of each layer from the core to the surface as fusion proceeds through successive stages. The codes are calibrated against observations of many stars at different evolutionary stages, against the properties of supernova remnants from stars that have already exploded, and against the outputs of nuclear physics experiments that determine the rates of the relevant fusion reactions. These codes have been refined over decades and generally reproduce the observed properties of stellar populations well in a statistical sense. Where they struggle is in predicting the behavior of individual stars precisely, because individual stars have specific histories, specific compositions, specific rotation rates and magnetic fields that introduce scatter around the average predictions. For Betelgeuse specifically, several inputs to the evolutionary models carry significant uncertainties. The distance is uncertain at roughly plus or minus 100 light-years, which propagates directly into the inferred luminosity and therefore the inferred mass and evolutionary rate. The current mass is uncertain because the initial mass is uncertain and the integrated mass loss over the star's lifetime is uncertain. The internal rotation rate is uncertain because the convective envelope obscures any direct measurement of the core's angular momentum. Each of these uncertainties affects the predicted remaining lifetime, and they compound rather than cancel because they are not independent. The theoretical precursor observables, the things that models predict might change in the external behavior of a star as it approaches core collapse, are also worth examining critically. The models that predict these signatures are built on the same physical assumptions as the evolutionary models. If those assumptions systematically mischaracterize the behavior of red supergiants like Betelgeuse, the precursor predictions may be correspondingly inaccurate. This is not a reason to dismiss the precursor framework. It is a reason to apply it carefully, and to remain open to the possibility that the actual precursors of core collapse in Betelgeuse may not exactly match the theoretical predictions built on models that have not been directly tested against a star that subsequently exploded. The only nearby supernova of the modern era for which pre-explosion data exists is SN 1987A. But the progenitor of SN 1987A was a blue supergiant rather than a red supergiant, a different type of object in a different evolutionary configuration. The pre-explosion images of the progenitor, identified in archival photographs taken before the 1987 explosion, showed a star that gave no obvious external sign of its imminent demise in the period leading up to the event. This does not mean there were no precursor changes. It means that with the data quality and monitoring cadence available at the time, no such changes were detected. What would have been visible with 2025-era instruments pointed continuously at that star in the years before its 1987 death is unknown, because the data does not exist. Betelgeuse is the first massive star in the modern era to be monitored with this intensity before its eventual explosion. Whatever sequence of events precedes its core collapse will be observed by the instruments currently running. Whether those observations will retroactively identify clear precursors that could have been predicted from the physics, or whether the final transition will appear sudden even in hindsight, is one of the most important open questions in stellar astrophysics. The monitoring of Betelgeuse is, among other things, an attempt to collect the data that would answer that question for future science. You do not need to understand all of this at once. The honest position from the researchers most familiar with the data is that the uncertainty has not been narrowed. In some respects, it has widened at the lower end. The pre-2019 comfortable picture of a well-understood star whose timeline was broadly accounted for no longer fully describes what the observations are showing. Assume it happens, not soon. But assume it happens. You are outside at night, in a place dark enough to see stars. Orion is up. You know where Betelgeuse is. You have found it 1,000 times. And then something is different. The point in the upper left shoulder is brighter than it should be. You look away and look back, still brighter. Over the next few hours it continues to increase. By morning it is still visible in the lightening sky. By noon it is a hard, bright point against blue, visible in full daylight, present alongside the sun. That night It is bright enough to cast shadows. Trees have shadow outlines pointing away from Orion. The horizon in that direction is faintly lit. But that is the second announcement. The first announcement happens underground roughly 3 hours earlier, before any change in the sky. The core of Betelgeuse collapses in approximately 1 second. In that 1 second, it releases more energy than our sun will radiate over its entire 10 billion year lifetime. 99% of that energy leaves the collapsing core not as light, but as neutrinos. Neutrinos pass through matter so weakly that a beam of them would cross a light year of solid lead and emerge on the other side with only a 50% chance of having been stopped. The neutrino burst crosses 700 light-years of interstellar space and arrives at Earth, while the visible explosion is still pushing outward through the star's outer layers, which is why the neutrinos get here first. In the Kamioka mine in Japan, the Super Kamiokande detector registers thousands of neutrino interaction events in 10 seconds. The ice cube detector at the South Pole, a cubic kilometre of Antarctic ice studded with 5,060 light sensors, sees a simultaneous brightening across its entire array. SNEWS issues an automated alert to subscribing astronomers worldwide. The direction, Orion. The confidence, high. The time remaining before visible brightening begins, hours. Every telescope with access to that part of the sky turns toward it. For several weeks there will be 2 suns. One will be ours, one will be a corpse. The last nearby supernova that produced a detectable neutrino burst was SN 1987A in the Large Magellanic Cloud, 168,000 light-years away, on February 23, 1987. 3 underground detectors recorded a burst of neutrino interactions within a few seconds of each other. The detection confirmed core collapse in real time, before most optical astronomers had even identified the brightening. SN 1987A at 168,000 light-years generated a detectable signal. A Betelgeuse supernova at 700 light-years would produce a signal roughly 58,000 times stronger. The detectors would be overwhelmed with events. The SNEWS alert would go out within seconds. The visible brightening begins hours after neutrino detection. The shock wave from the core collapse, working its way outward through the stellar envelope, breaks through the surface in a flash of X-ray and ultraviolet radiation. Instruments in space would catch this shock breakout signal before human eyes registered any change. Then the main optical brightening begins. Peak brightness, estimated between apparent magnitude -9 and -12, depending on the model. The full moon sits at magnitude -12.7. A Betelgeuse supernova at peak would be comparable to a full moon, present in the sky at all hours, visible in daylight, casting actual shadows on the ground at night, bright enough to read by barely, if you positioned yourself correctly. The horizon in the direction of Orion, lit at 3 in the morning. We have covered a lot of ground. Take a breath. The peak lasts weeks. The fading takes months. The light curve is powered in its later phases by the radioactive decay of nickel-56, produced copiously in the explosion and decaying first to cobalt-56 and then to stable iron-56. Each decay releases gamma rays converted by the expanding ejector into visible light. The sequence of events between the neutrino burst and peak brightness deserves careful description because it involves several distinct phases that astronomers have predicted from physics but have never observed in a nearby star at this cadence. Hours 1 through 12 after neutrino detection. The shock wave from core collapse continues working outward through the stellar envelope. This is invisible from Earth except in the neutrino channel. Astronomers worldwide, alerted by SNEWS, have redirected every available instrument toward Orion. Ground-based optical telescopes are pointed and waiting. Space-based X-ray and ultraviolet observatories are already monitoring. Hours 12 to 24. The shock wave approaches the photosphere. Immediately before it breaks through, the material ahead of it is heated to extreme temperatures and compressed. This heated surface material begins radiating in X-ray and ultraviolet wavelengths before the shock actually emerges. Space-based instruments detect a precursor brightening in high-energy radiation. The shock breakout is imminent. Hours 24 to 48. The shock breaks through the photosphere. An intense flash of X-ray and ultraviolet radiation, the shock breakout signal, lasts from minutes to hours. This would be the brightest transient X-ray event visible from Earth since the dawn of X-ray astronomy. Space-based instruments capture it in real time. Ground-based optical observers begin seeing the first hint of visible brightening. The star is no longer a stable orange point in Orion. It is changing visibly on a timescale shorter than human attention spans are accustomed to for astronomical objects. Days 2 through 7, the visible brightness climbs rapidly toward peak. The star goes from naked eye visible and unusual to daylight visible. By day 3 or 4, it would be the brightest object in the sky after the sun. People in the street would notice. People who never thought about astronomy would look up because something in the sky is wrong, and wrong in a specific direction. And when they look that direction, they see something bright enough to make their eyes water slightly even in daylight. Peak and beyond. For 1 to 3 weeks, at or near maximum brightness, the supernova dominates. It is present at all hours. It is in the daytime sky. At night it is brighter than the full moon. The shadows it casts are softer than moonlight shadows because it is a point source rather than an extended disk. But they are real, definite shadows, visible on any flat surface when you position yourself between the light and a wall. Every camera pointed at the sky includes it automatically. Every photograph taken outdoors captures a second light source in the sky. The experience of living through a nearby supernova is not in the astronomical literature because it has not happened in recorded history at this brightness. The last supernova clearly visible to the naked eye, Kepler's supernova in 1604, reached magnitude negative 2.5 at peak, far dimmer than a Betelgeuse supernova would be. The 1006 CE supernova, the brightest in recorded history, reached perhaps magnitude negative 7.5 and was documented across multiple cultures as visible in daylight. A Betelgeuse supernova at magnitude negative 9 to negative 12 would exceed even that event. The human experience of a nearby supernova is something that requires active imagination because no living person has witnessed one at this brightness. The closest historical analogue with significant documentation is SN 1006 in the constellation Lupus, which occurred on April 30th, 1006 CE and reached an estimated peak apparent magnitude of negative 7.5. Contemporary accounts from China, Japan, Egypt, Iraq and continental Europe describe it as visible in daylight, as bright as a quarter moon at night, bright enough to read by, and visible for at least 2 years before fading below naked eye visibility. A Betelgeuse supernova at magnitude negative 9 to negative 12 would exceed even SN 1006. The SN 1006 documentation describes the population's response. Confusion, fear in some quarters, astronomical records made with urgency by scholars who recognized they were witnessing something without precedent in their lifetimes. In 1006, there was no framework within which to understand what a supernova was. There was only the sky doing something wrong, conspicuously and persistently for months. In 2026, or whenever the event occurs, the framework exists. The snooze alert will go out hours before the visible brightening. Astronomers will know what is happening. The public will be told. There will be news coverage before the sky changes, and then the sky will change, and all the preparation and explanation will encounter the simple fact of standing outside on a clear night and seeing a star that was not there yesterday, or rather, seeing a star that was there but has become something entirely different overnight, bright enough to make shadows, present in the daytime, real in a way that all the numerical descriptions of it had not quite conveyed. For roughly a year, a point far brighter than any other star would remain in Orion's shoulder, slowly dimming, never quickly. The SN 1987A detection confirmed, in the most direct possible way, the theoretical model of core collapse. The model predicted that core collapse would release roughly 10 to the power of 46 joules of energy, primarily as neutrinos in a burst lasting approximately 10 seconds. The detected burst was consistent with that prediction. The delay between the neutrino burst and the visible brightening, caused by the shock wave taking hours to work through the stellar envelope, was also consistent. 24 neutrino interactions from a star 168,000 light-years away confirmed decades of theoretical work in real time. A Betelgeuse supernova at 700 light-years would produce a signal 58,000 times stronger. Super Kamiokande would register hundreds of thousands of interactions. IceCube would register millions. The detectors would operate in a saturation regime they have never experienced. The scientific yield from the neutrino burst alone, before any optical data was collected, would be extraordinary, constraining the equation of state of nuclear matter at densities that no terrestrial laboratory can produce. SNEWS, the Supernova Early Warning System, was established because of the SN 1987A experience, and because the list of nearby massive stars capable of producing a detectable neutrino burst is short and includes Betelgeuse prominently. SNEWS 2.0, operational since 2022, added detectors, improved algorithms, and refined alert protocols. The paper establishing SNEWS 2.0 explicitly names Betelgeuse as a primary motivation. The people building this infrastructure have concluded that the probability of a galactic supernova is high enough to justify continuous investment. They have not specified a probability for Betelgeuse specifically. They have built a detection network that will catch the signal if it comes. Everything the star had kept hidden behind thousands of kilometers of opaque plasma would be broadcast outward in the spectrum of its death. The chemical composition of successive layers, the products of each burning stage, the internal density structure, all of it disclosed in the evolving light. Every observatory with access to the northern sky would read it in real time, a disclosure that would take decades to fully analyze and that would answer questions the current monitoring cannot approach because the core is not observable from outside. After the light fades, something remains, and something is permanently absent. The explosion expels between 8 and 15 solar masses of stellar material outward at velocities between 5,000 and 10,000 kilometers per second. This material does not stop. It expands into the circumstellar environment, sweeps up and compresses the layered shells of previously ejected material that post-2020 observations have mapped in such detail, and then continues into the interstellar medium. Over decades and centuries it slows and forms a supernova remnant, a glowing nebula of shocked gas and heated dust. At Betelgeuse's distance, the remnant would be visible in binoculars and spectacular through any telescope, a faint expanding bubble of light in the direction of Orion for hundreds of years. Orion will have a hole in it, not a gap, a wound. The 8-star pattern that has existed unchanged for every generation of human beings will become a 7-star pattern. Future generations will learn a different Orion. They will trace the belt, the sword, the remaining stars, and they will not notice the absence because they will have no memory of the presence. The sky you have been seeing your whole life, unchanged since your earliest memory, unchanged for all of recorded history, will have been permanently altered by the death of a specific object 700 light-years away. At the center of the remnant, physics makes a final decision. If the collapsing core remains below roughly 2 to 3 solar masses, it stabilizes as a neutron star, an object perhaps 20 kilometers across containing more mass than the Sun. The density is so extreme that a teaspoon of neutron star material weighs approximately 10 million tons at terrestrial gravity. The gravitational field at its surface is 100 billion times stronger than what you feel standing on Earth right now. A neutron star born from core collapse typically spins rapidly, from a few rotations per second to dozens, because angular momentum is conserved as the core collapses from Earth-sized to city-sized. If its magnetic poles are misaligned with its rotation axis, the strong magnetic field channels radiation into beams that sweep around as the star rotates. If one of those beams crosses Earth's line of sight with each rotation, we see a pulsar, a metronomic radio source clicking at the neutron star's spin frequency. The Crab Nebula in Taurus is exactly this, the remnant of a supernova observed in 1054 CE by Chinese and Arab astronomers who recorded it as visible in daylight for 23 days and bright at night for nearly 2 years, contains at its center a pulsar spinning 30.2 times per second, still clicking nearly 1,000 years later, losing rotational energy slowly, slowing gradually. A Betelgeuse pulsar from a star 9 times closer than the Crab's progenitor would be studied with instruments incomparably more capable than anything available in 1054. The universe does not need you to rush through this. If the core mass exceeds the threshold, the collapse does not stop. Neutron degeneracy pressure fails. The matter falls through it and continues to a singularity. A black hole forms, invisible except through its gravitational influence on surrounding material. No pulsar, no visible central object. In the direction of what was Betelgeuse's shoulder, a wound in Orion, and at the center of the expanding remnant, an absence. The permanent alteration to Orion is worth contemplating because it represents a change to something that has been stable for longer than any human institution. The 7 stars that form the recognizable outline of Orion, the 3 belt stars, the 2 foot stars, the 2 shoulder stars, have been in their current relative positions for at least 100,000 years, long before the evolution of modern human cognition, and certainly long before any writing or systematic record-keeping. Prehistoric rock art in various regions has been interpreted as depicting constellations, including Orion, suggesting recognition of this pattern by human beings who lived before agriculture, before cities, before any continuous civilization. The shape has persisted across every culture that has ever had a clear night sky. When Betelgeuse explodes, the shape changes. Within weeks, the left shoulder will be orders of magnitude brighter than any other star. As the supernova fades over months and years, the shoulder will dim below naked eye visibility, and Orion will have 7 prominent naked eye stars instead of 8. The belt, the sword, the remaining stars will persist, but the left shoulder will be empty. Future generations will inherit this changed sky. If the explosion occurs within living memory, those who see it will remember both versions. If it occurs in tens of thousands of years, no living memory will carry the transition, and the historical records will preserve it as a fact but not a felt experience. Either way, the Orion that exists in every human culture, every mythology, every astronomy textbook, every photograph taken before the explosion will become a historical artifact, a version of the sky that once existed and no longer does. The record we are building now, the detailed photometric and spectroscopic and interferometric observations, accumulated over years of intensive monitoring, will itself be valuable after the explosion. Future researchers trying to understand the explosion mechanism and the progenitor's evolutionary state will have access to pre-explosion observations of unprecedented quality and breadth. Every monitoring program running today is contributing to that record. The researchers doing this work may not live to see the payoff. The work is being done anyway. There is a gap between what researchers say in papers and what they say when the recording has stopped. This is not concealment. It is how scientific communication is supposed to work. Papers must be falsifiable. Claims must be proportional to evidence. We are worried about this star cannot appear in a peer-reviewed journal without being translated into specific, operationalized, testable language. What the translated version looks like is, the data deviates from baseline expectations. The circumstellar structure is not consistent with steady-state mass loss models. Further monitoring is warranted, consistent with a more advanced evolutionary state than commonly assumed. The star itself did not change in any way that can be directly seen between any two individual observations. Its change is revealed only in the aggregate, only when the full record is examined across years. This is the nature of slow processes in stars. They are invisible in any single frame. They are legible only in the sequence. No astronomer has said it is about to explode. None of them have said it is not. That sentence is not equivocation. It is the exact shape of the uncertainty. The models most commonly cited place Betelgeuse at thousands to hundreds of thousands of years from core collapse. Those same models failed to predict the Great Dimming, failed to reproduce the post-dimming pulsation behavior, failed to account for the elevated mass loss rate. A model that has been wrong in one direction can be wrong in another. The confidence interval around any remaining lifetime estimate has not been formally tightened since 2020. In some interpretations, it has loosened at the lower end. The theoretical precursor signatures for core collapse in a massive star are known and have been discussed in the literature, shortening of pulsation periods as the internal structure evolves, increasing convective turbulence as the outer envelope becomes less thermally stable, elevation in mass loss rate as pulsation amplitude grows, changes in circumstellar dust emission as ejection events become more frequent or more massive. Every item on that list corresponds to something observed at Betelgeuse since 2019. No single observation confirms a pre-collapse interpretation. The pattern as a whole is consistent with one. If you're listening in the dark, let that image rest with you. In early 2026, the paper analysing the newest Webb circumstellar data included language stating the multi-shell structure was most readily explained by episodic mass loss events of increasing frequency, and that this pattern would be consistent with an object in a more advanced evolutionary state than commonly assumed. That language appears in a peer-reviewed paper only when the authors believe the data supports the interpretation, regardless of how many hedges surround it. The hedges are real. So is the interpretation. What the community is watching for is a signal that would shift the probability assessments enough to change the conversation. Pulsation period continuing to shorten. Mass loss rate continuing to elevate. Additional shells detected at intermediate distances. Changes in the infrared excess from dust emission that suggest increasing ejection frequency. These signals may never arrive, or not for tens of thousands of years, or they may arrive in the next monitoring cycle. The data is being collected. The analysis is ongoing. The word in the title of this script is not dramatic framing applied to straightforward science. It is the accurate description of the cognitive state of the people who know this data best. Quietly, not loudly, not publicly, not in press releases. Quietly, in the monitoring programs that have been running continuously since 2020. In the careful language of papers that translate concern into falsifiable statements. In the conference hallway conversations after the session ends. In the decision to keep every available instrument pointed at one star in Orion, rather than somewhere else. A specific technique from the competitor scripts is useful here, one called duration inversion. take an acceptable short-term rate and multiply it by an extreme duration to reveal the hidden consequence. Consider the mass loss rate. Betelgeuse's pre-2019 mass loss rate, estimated from stellar wind observations, was roughly 1/10,000th of a solar mass per year. That sounds trivially small, but apply it over 10,000 years, the lower bound of the current remaining lifetime estimate, and the star sheds 1/10th of a solar mass from its envelope in that time. Over 100,000 years it sheds a full solar mass, the mass of the Sun, lost through stellar winds, while the star continues burning toward core collapse. This continuous mass loss, maintained over the timescales involved in stellar evolution, strips the envelope progressively, changing the density structure that the eventual shock wave will propagate through, and modifying the characteristics of the supernova remnant that forms. Now consider the post-2020 elevated mass loss rate. If the circumstellar observations accurately reflect a rate higher than the pre-2019 baseline, even by a factor of 2 or 3, the amount of mass shed over the remaining lifetime changes accordingly. A higher mass loss rate before core collapse produces a more massive circumstellar environment for the shock wave to interact with, more infrared emission from dust heating as the wave expands outward, and a modified chemical composition in the pre-supernova envelope that leaves different spectroscopic signatures in the light of the explosion. The monitoring programs running now are not idle while waiting for the explosion. They are building the pre-explosion dataset that makes the explosion scientifically interpretable when it occurs. Every mass loss observation added to the record now is a data point that future astronomers will use to understand what they are seeing in the light of the dead star. They are quietly worried. The communication gap between the professional Betelgeuse science community and the general public mirrors a broader challenge in translating ongoing scientific uncertainty into terms that are both honest and useful. The Great Dimming story was easy to cover because it had a clear narrative arc. Something dramatic happened, scientists tried to explain it, the star recovered, the explanation was found. That arc fits a news cycle. The post-recovery anomalies do not fit the same arc because they do not have a resolution. They are ongoing. The story does not close. When a story does not close, when the data keeps accumulating and the conclusion keeps being deferred, science communication tends either to drop the story or to overstate the available evidence in the direction of the more dramatic interpretation. Neither is accurate. The Betelgeuse situation is genuinely ambiguous in a scientifically interesting way, and the ambiguity itself is the story. A star whose behavior the best available models do not fully account for, accumulating anomalies in one direction across multiple independent observational channels, is a star that deserves continued attention precisely because the situation is unresolved. The researchers continuing to monitor Betelgeuse in 2026 are not monitoring it because they believe an explosion is imminent. They are monitoring it because the current observational picture is incomplete, the models are insufficient, the anomalies are real, and the scientific value of the pre-explosion data set is enormous, regardless of when the explosion occurs. What makes the situation worth understanding is not the possibility of catastrophe. It is the honest picture of what scientific uncertainty looks like when it is being taken seriously. The people watching this star are not certain. They are not dismissive. They are collecting evidence, testing hypotheses, updating models, and continuing to watch something that has surprised them once and might surprise them again. And they have not found a reason to stop. The specific scientific value of the current monitoring, independent of the question of when the explosion occurs, is worth establishing, because it is often overlooked in discussions that focus entirely on the supernova timing question. Every observation of Betelgeuse added to the pre-explosion dataset increases the scientific yield when the explosion eventually happens. Stellar astrophysicists who will be working on core collapse supernovae in 2200 or 2500, whenever the event occurs, will have access to a century or more of intensive multi-wavelength monitoring of the progenitor star. They will know its pulsation behavior in detail, including how that behavior changed over the years and decades preceding the explosion. They will know its mass loss history from circumstellar shell observations. They will know its surface temperature and luminosity history from photometric and spectroscopic monitoring. They will know how its neutrino flux from normal fusion compared to background through whatever detector improvements exist by then. None of this data exists for any previous core collapse supernova. SN 1987A's progenitor was identified in archival photographs taken before the explosion, but those photographs were not taken with monitoring in mind and have limited utility for extracting pre-explosion variability information. Every other supernova in the historical record has a progenitor known only from a single pre-explosion image at best, with no dynamic baseline of behavior to compare against. Betelgeuse will be the first core collapse supernova for which the pre-explosion state is known in comprehensive detail. The questions that the pre-explosion data will allow future researchers to answer about what the surface was doing in the final phases of the star's life, whether clear precursors emerge in retrospect even if they were ambiguous in real time, how the mass loss history connects to the characteristics of the explosion and the remnant, are questions of fundamental importance to stellar astrophysics and would advance the field by decades. This is not a speculative future benefit. It is a predictable one. The data is being collected. It will be there when it is needed. The researchers collecting it now are not motivated primarily by the hope of witnessing the supernova in their lifetimes. Most of them expect the explosion to occur well after any of them are alive. They are collecting data because it is the right thing to do for the long-term progress of the science. This kind of long-horizon scientific investment, building data sets that will matter to people not yet born, is one of the less celebrated but most important aspects of observational astronomy. You do not have to expect to see the payoff to recognize that the work has value. The word quietly is doing more work in this story than it might appear. Scientific concern is almost always expressed quietly, because the alternative, expressing it loudly, carries costs that the professional community is trained to avoid. Loud claims that turn out to be wrong damage credibility. Loud claims that require subsequent retraction erode public trust. And in a domain like stellar astrophysics, where timelines are measured in thousands to hundreds of thousands of years, this star might explode sooner than we thought, is a claim that can sit unconfirmed for the entire professional lifetime of anyone alive today. There is no feedback mechanism fast enough to validate or invalidate the concern in any individual career, so the concern is expressed quietly, in the language of peer-reviewed papers, in the decision to keep monitoring resources pointed at one specific star in one specific constellation, in the maintenance of a global neutrino alert network whose primary motivation is a small handful of nearby massive stars, of which Betelgeuse is the most prominent, in the choice to build the Webb observation program that produced the 2025 and 2026 circumstellar shell results. None of these are the actions of a community that believes everything is fine and the star will persist unchanged for 100,000 more years. They are the actions of a community that has seen something unusual, does not fully understand it, and has decided that the appropriate response is to watch more carefully. That response, quiet and sustained and institutionally serious, is what the word quietly in the title of this script is pointing at. Not a dramatic underground whisper, not a suppressed alarm. The ordinary professional seriousness of people who have observed something that their models do not fully explain, and who have collectively decided without fanfare or announcement that the observation is worth taking seriously. That is what quietly worried looks like from the inside. and from the outside, from your position tonight looking up at the warm orange point in Orion's shoulder, it looks like any other star in any other familiar constellation, making any other ordinary light. The JWST observations from 2025 and 2026 represent the most sensitive probe of the region immediately surrounding Betelgeuse ever conducted, and their implications for the star's recent mass loss history extend the picture in ways that were not anticipated when the observation programs were designed. When Webb was pointed at Betelgeuse, the primary goal was to characterize the structure of the dust emission from the innermost circumstellar shells with mid-infrared sensitivity that no prior instrument could provide. The discovery of the third, previously undetected shell between the two known structures was not an expected result. It was found in the data after the fact, when the analysis revealed a faint excess of mid-infrared emission at an intermediate radial distance from the star that was inconsistent with the two-shell model that had been the consensus. The third shell's inferred ejection date in the mid-1800s places it in the same era as Herschel's anomalous observations. This correspondence is suggestive but not proven. The dating carries uncertainty of perhaps several decades, wide enough that Herschel's specific observations in 1836 and 1840 fall within the uncertainty range but not uniquely consistent with the shell's inferred age. A rigorous connection between the Herschel observations and the third shell requires either a more precise age determination from the shell's current position and an assumed outflow velocity, or additional historical records from the 1830s and 1840s that could constrain what the star was doing during that period more precisely than Herschel's visual comparisons allow. Those historical records, if they exist, would most likely be found in the archives of variable star observing societies, observatory logbooks, and the correspondence of working astronomers of that era. The search for such records, motivated by the Webb discovery, is one of the minor but genuine scientific follow-up activities that the 2026 circumstellar analysis has generated. The possibility that a 19th century observation and a 21st century space telescope image might together constrain the history of a star 700 light-years away is one of the small specific pleasures of how science accumulates across time. The neutron star or black hole left behind after the explosion is, in a specific sense, what all the monitoring data is about. The current observational puzzle, which internal burning stage has the core reached, which end state will the collapse produce, cannot be resolved until the explosion happens and reveals the answer in the characteristics of the light and the compact remnant. All of the monitoring, the pulsation tracking, the circumstellar mapping, the radial velocity monitoring, exists in the space before that revelation. It is the most complete possible preparation for an event that will answer the underlying questions definitively, but that cannot be predicted precisely in advance. There is something appropriate about that structure. The best science often proceeds this way, accumulating detailed characterization of a system whose most important properties can only be measured at a moment of extreme change that has not yet arrived. The geologists who study fault systems in seismically active regions characterize the accumulated stress and the locking depth and the recurrence interval of past earthquakes, knowing that the earthquake itself will reveal something their pre-earthquake data could not. The meteorologists who track developing hurricanes characterize the sea surface temperatures and atmospheric conditions, knowing that landfall will test their model against the physical reality. The Betelgeuse monitoring community is in the same position. They know the star well. They do not know it as well as they will after it explodes. They are building the pre-explosion dataset that will make the post-explosion science possible. This patient accumulation of context carried out by researchers who understand that they are preparing for an event they will likely not live to see represents one of the most human things that science does. It transmits knowledge and investment across generations. The observations being made now in 2026 will be used by astronomers in 2026 or 2426 or 26 and 26 to understand an explosion that may not have occurred yet. The work matters forward in time in a way that does not require the people doing it to be present for the payoff. That is what it looks like to take the long view of a short human life spent inside an ancient universe. Go outside on a winter night and find Orion. You know how. The belt, the sword below it, the point at the upper left shoulder, the warm reddish-orange one that has been in the same place since before any record you or anyone you've ever known could trace. Historical specificity anchors help translate the star's timeline into something human experience can hold. The light reaching your eyes from Betelgeuse tonight left the star roughly 700 years ago. In 1325, when those photons began their journey, the following was true on Earth. The Aztec Empire was just being founded. Dante Alighieri had died 4 years earlier. The Ottoman Empire was in its third decade. The Black Death had not yet reached Europe. The 100 Years' War between England and France had not yet begun. The Renaissance was 2 generations away. No European had crossed the Atlantic. No printing press existed. The entire accumulated written knowledge of humanity fit in a handful of monasteries. Everything that has happened since, all of it, the Renaissance, the Reformation, the Scientific Revolution, the Age of Oceanic Discovery, the Industrial Revolution, the World Wars, the Space Age, the Digital Age, all of modern civilization's development in every direction, occurred after those photons left the surface of Betelgeuse. And the photons carrying that information, having crossed 700 light-years of empty space, land in your eye tonight as a warm orange point and register as a familiar star in a familiar constellation. The 2019 mass ejection event, whose light and consequences we've been observing and analysing for the past several years, actually occurred in the early 1320s by the calendar of events happening on Earth at the time. The monitoring results we are currently producing from ground-based and space-based observatories reflect the behaviour of Betelgeuse as it was during the 100 Years' War. The researchers analysing the 2026 Webb data are looking at a star as it existed when the plague was still reshaping the demographics of Europe. This is what distance means as a scientific constraint. Every measurement is a measurement of the past. The present state of Betelgeuse is unknown and unknowable by any means currently available. What we are characterizing is its history, delivered at the speed of light, and drawing from that history the best available inferences about a present we cannot directly observe. The light reaching your eye right now left Betelgeuse roughly 700 years ago. The 1300s. The Black Death had not yet reached its European peak. The Ottoman Empire was consolidating its early territory. Dante was writing the Commedia. That photon left the surface of this star, entered the vacuum of interstellar space, and has been crossing the 700 light-years between Betelgeuse and Earth ever since, travelling at 300,000 kilometers per second, arriving tonight at your eye as a point of warm orange light in a dark winter sky. What you're looking at is not Betelgeuse as it is. You are looking at Betelgeuse as it was. The star you see tonight may already be dead. The core may have collapsed. The neutrino burst may already be in transit, crossing the interstellar medium at the speed of light, still years or decades or centuries from arriving. If Betelgeuse collapsed in the 1800s, the announcement of that fact is en route and has not yet reached us. The orange point in Orion's shoulder would still be there, looking normal, sending the light of a star that no longer exists. There is no way to know. The sky displays the past in the present tense, and the two are indistinguishable without receiving a signal that crosses the gap. Thank you for spending this time here tonight. If this video gave you something worth keeping, a subscribe or a like helps this channel find more people who want exactly this kind of quiet evening. It genuinely matters. The warm orange shoulder has been there for every generation of human beings who ever looked up. The Babylonians catalogued stars in its region. Medieval navigators used Orion to orient themselves at night. Every person who has ever stepped outside on a clear winter evening in the northern hemisphere has seen it in the same place, making the same light. Until the night when it is not dim and familiar, but brilliant and wrong, and the sky has a different weight to it, and children ask adults what happened and most adults do not have words. And then across the months the light slowly fades, and what is left is a wound in a constellation that never had one, and future generations learn that sky is the only sky there has ever been, and they trace out the 7 stars of Orion without knowing there was an 8th, without knowing what it looked like, without knowing that for all of recorded human history, a warm orange point called Betelgeuse sat at the upper left shoulder of the hunter and made light. The philosophical dimension of observing something that may already not exist is worth sitting with rather than hurrying past. Every observation in astronomy is a historical observation. The moon we see is the moon as it was 1.3 seconds ago. The sun is 8 minutes in the past. The nearest star beyond the sun is 4.24 years old by the time its light reaches us. Andromeda is 2.5 million years old in the light we see. The most distant objects in the James Webb Deep Field images are seen as they were more than 13 billion years ago, when the universe was a small fraction of its current age. Betelgeuse at 700 light-years falls somewhere in the middle of this range, close enough that the time lag is measured in centuries rather than millions of years, but far enough that the star we observe has already experienced 700 years of additional history before we receive any word of it. This lag is not a limitation that better technology will overcome. It is a fundamental feature of a universe where information cannot travel faster than light. No telescope, however large, no instrument, however sensitive, will ever observe the current state of a star at 700 light-years. The best any instrument can do is observe the state of that star 700 years ago with increasing clarity and precision. This means the question of whether Betelgeuse is currently alive or dead, in the sense of whether its core is still fusing silicon or has already collapsed, is a question that cannot be answered from Earth in 2026, not because we lack the instruments, because the information about the present state of the star's core has not yet reached us. We are always 700 years behind the news. When the core of Betelgeuse does collapse, the neutrino burst will announce it within hours of that event. Those neutrinos will cross 700 light-years in 700 years and arrive at Earth with the news 3 hours before the visible explosion lights up the sky. In that 3-hour window between the neutrino alert and the visible brightening, every observatory on Earth will be pointed at Orion. Every detector will be running. The moment the light arrives, it will be observed with more instruments and more precision than any other event in astronomical history. Until then, the orange point persists in the same place it has always been, making the same light, carrying the same history in its spectrum, and possibly already gone. The news in transit, the announcement coming, the instruments waiting. The orange light that leaves Betelgeuse every second contains information about the star's surface temperature, chemical composition, and velocity structure that instruments can read. But it does not contain information about what is happening in the core. The core is sealed behind thousands of kilometers of opaque plasma, and the only signal from it that can reach Earth without passing through those layers is the neutrino flux, too faint to measure at this distance under normal fusion conditions, and detectable only in the catastrophic amplification of core collapse. This means the researchers watching Betelgeuse are, in a specific and somewhat strange sense, watching the outside of something they most want to see the inside of. Every observation is a measurement of the surface expression of interior processes that remain hidden. Every model is an attempt to infer the hidden interior from the visible exterior. Every anomaly is a data point in an argument about something that cannot be directly observed. The science is necessarily indirect, necessarily inferential, necessarily incomplete, until the moment the core speaks for itself in a burst of neutrinos that underground detectors around the world will hear at the same instant. Until that moment, the orange point will be there, making light, sending photons that left 700 years ago and will continue arriving on Earth for another 700 years after whatever happens in the star's core tonight. Whether or not the core has already spoken, whether or not the message is already in transit, whether or not the answer to everything the monitoring programs have been asking is currently crossing the interstellar medium at 300,000 kilometers per second, approaching an Earth that does not yet know to expect it. The instruments are running. The sky above you remains exactly as it has always been. And somewhere in the 700 light-years between here and the shoulder of the Hunter in Orion, the answer is either still forming or already quietly on its way. And then one winter night someone asks, "What was that star called?" And nobody in the room knows anymore. The rest of the dark is yours. Good night.